Okay, ham radio fans, it's K8BYP back in the shack after being in the basement cutting and filing metal, making a plate to mount the 4 switching power supplies on the back of the HP 8660 generator. But the topic du jour is, I'd mentioned recently the idea of transmission line length makes a difference. It does. Longer transmission line has more loss. Why use 200 feet and get 6 dB loss when we could use 50? That's pretty obvious. But I'd mentioned the idea of some hams cut their transmission lines to even or half wavelength increments, and that I wasn't sure at the time exactly why that was. So I did some thinking, did some studying, and have figured it out. So I'm going to lay it on you. Everybody, including the CBers, knows about going someplace in transmission line, maybe by the transmitter, and putting in a so-called SWR meter and reading SWR to see if the antenna is matched. That's just full of errors. And one mistake the CBers make is pretending that adding some transmission line to effectively move where the SWR meter is and having the SWR meter read a low value means they matched something. And that is absolute foolishness. All that's done is fool them into thinking they improved anything and added some transmission line losses and some more energy loss due to maybe some more connectors reflecting. It's very important. If you haven't seen my video on why SWR meters aren't, SWR is standing wave ratio, usually VSWR, voltage standing wave ratio. And a ratio is a quotient of two numbers. A ratio of 10 is the number 10 divided by the number 1. In radio, that ratio used to be using a light bulb and a loop of wire on open line transmission line to find where there are voltage minimums and maximums. And that was originally what VSWR was. With our modern SWR meters, we can't do that. They measure at a single point, so there's no ratio. So the ratio then is the ratio of, at that point in the line, the forward RF current versus the reflected RF current. The goal is 0 reflected RF current. When there's an antenna feed point mismatch, and there's a significant amount of reflected energy, enough that there's a reading possible at the transmitter over the transmission line loss. If it's a few tens of milliwatts, there may not be enough surviving back to the transmitter to measure, and it doesn't make any difference. That's trivial. But if there's a lot of mismatch, then the length of the line becomes important, because the way to look at that is that the line is being phased. And phase is a ratio or proportion or relationship between several or more things, kind of like a ratio. The phase of a sine wave is reckoned from 0 degrees, or the 0 voltage at the baseline. And the first peak is a plus 90 degree phase, and the second minimum at the 0 line is the 180 degree phase. That's relative to 0, so that's a phase. But in this instance, there's a phase relationship between two separate mathematical functions, the forward wave and the reflected wave. And in this diagram, assume that these are currents, because that's what the so-called SWR meter is reading. It's reading RF current. If the length of the transmission line is not properly phased, I don't think the proper term is matched. Match implies the correct resistive value. But if it's phased so that it's not multiples of a half wavelength long and exactly, then that reflected energy will effectively be out of phase with the incident energy and could result in something like this, where the forward is the solid sine, actually cosine, that's a cosine wave, starting on the left above the AC source with the peak. That's the forward or incident wave, and a reflected wave is dashed. And if that line isn't the correct length, then the reflection will occur at a point that's not a minimum or a maximum, relatively speaking. So at some point where the meter's put, with the vertical dash line T, then the meter will read forward current at that point in time and on a line of almost maximum incident current, which is near the top of that cosine wave. But it's going to read maybe an eighth of the reflected current, way down there at the bottom of that dashed line. They're both cosine lines. But you can see the ratio, the indicated ratio will look quite good because the meter's seeing much more forward current than reflected, when in reality the reflected current is about the same magnitude as a forward, and SWR is infinity. And if this occurs at the transmitter, it can destroy the transmitter. And I have a video on that about how antenna system mismatches can destroy modern solid-state rigs. This was not so much a thing in tubes. With tube transmitters, like the TR3 hiding under its blanket, saw an antenna system mismatch. Then we just look at the tubes and see the plates glowing brown or red, and we say, uh-oh, something's wrong in the antenna. The analogy to that in solid-state radio is saying, uh-oh, we got to take it apart and replace fried final transistors and transformers, because there can be such high peak voltages and currents that destroy the output of a solid-state transmitter. And that's why the controllers in those radios scale the power back so that doesn't happen. So I guess the short answer is it's necessary to get the transmission line in multiples of half wave, and preferably exactly, so that we get the reading at the transmitter with the fake SWR meter that's as close to what it would be at the feed point, not counting transmission line losses. Because realize there are two losses, one forward, one reverse. It's the same, the energy is traveling both directions over the same line with the same losses. So the indicated so-called SWR at the transmitter will always be less than what it is at feed point. But the beauty of this is suggested in what I've done and what Charles out in Washington State is doing right now. He's put up a dipole and he's rigging a nano at the feed point with a powered USB cable and a computer, and he's going to do feed point testing, and he's really getting into this. And in theory, this transmission line phasing would eliminate the need or reduce the need to measure at the feed point, or at least give as close as we can reasonably get to doing it at the feed point. That becomes very difficult when the antenna's at 60 feet. Rig Expert came out with a gadget that fastens on the feed point and sends back by, I think it's Bluetooth link, the data. $180. Really not bad, a little high for what it is, but it's niche product. It's going to be high. But that is the correct way to do it. Go out to an AM broadcast tower, measure at the feed point at the base, not in the transmitter room. But when the feed point is where we can't get to it, or if we have physical limitations like a bad leg or bad back or some such thing that we can't do that, then this kind of thing becomes important. In my work and study with antenna emission due to charge compression, I use the terms collision, acceleration. That's my view on the topic. But I suspect there may be also benefits to having this phasing correct for maximum emission, but I can't prove that, so I'm not going to go any further down that road. Now there's a sneaky little observation that kind of sort of makes this problem disappear. We have to start from the viewpoint that no SWR is acceptable. It's, the feed point has to be R50 for a 50 ohm line. Then that's it. And the antenna only works where it's R50 or very little apparent reactance. If that's the case, then all this goes away. And this is why I'm harp so much on getting the feed point just right. It makes all this mess disappear. But for initially setting an antenna up, it's pretty unlikely that we're going to get it right the very, very first time. And we can use relative measurements like tuning the transmitter up and down to see whether the SWR indicator goes up or down as the frequency goes up or down as an indication of what to do for lengthening or shortening a wire by frequency. That doesn't tell us necessarily about raising or lowering the antenna for the correct feed point resistive value. But there's a very sneaky thing happening that's very easy to miss unless we know the old-timers trick of looking at a meter with a magnifying glass. In the old days with mechanical meters, when we wanted to see a very small quantity, we put a magnifying glass up against it and made the measurement to see if there's a little bump in the needle we can't see without the magnifying glass. And some meters had magnifiers in them. But the observation that saves our chinny chin chins and makes this simple is that when the feed point is correct, there is no reflected energy. So there will be no reflected current. Well, that's never the case. And that's related to the factor called return loss. You'll probably see that on an analyzer, return loss of 23 dB or 35 dB. That return loss implies how much energy is coming back to the transmitter. And at 30 dB, that's, 1,000 times less, so it's trivial. A return loss of 9 dB is not good. But when there is a mismatch, here's the key, and it's not obvious. But when there's a mismatch, everywhere on that line at all times, there will be some current. Fart around with a fake tuner, the indicated SWR might go down to 1.2, but that proves there's no match. Because when there's a match at the feed point of the antenna, there's none returned, not a little bit. So what indicates a correct match at feed point is 0 indication. Key the transmitter, the thing doesn't move. The indication is not that it moves a little bit, and we just say that's okay, because it isn't. Because my experiments here show that a little mismatch is a very bad thing. No, it doesn't result in a tremendous loss of energy transfer to the antenna, but it can change directionality. And there's the key. Now, for the first time ever, I have exactly phased the transmission line on my 15-meter dipole. It is exactly 2 wavelengths long. And I did that on the mega expensive Tektronix TDR, $10,000 TDR unit. Very few of us have that. Very few of us would have any other use for it. It's mainly a research tool. The practical way to approach it is to find the stated velocity of the line. For polyethylene, it's 0.67. It's not a real accurate number, but it's better than nothing. And use that factor to cut the transmission line to half-wave intervals. Like the antenna wires, like reducing the length of the wire for the velocity through air of 0.951. The velocity of the transmission line is slower because the EM fields are going through a solid dielectric, such as foam or polyethylene or Teflon. And that material slows down the wave propagation. So therefore, the line has to be shortened by a factor of whatever the half one half 2 wavelength distance is at speed of light, multiplied by the velocity factor of the line. They'll get pretty close. The measurement I made on the 15-meter dipole was 0.677. That's dead nuts accurate. The stated value for polyethylene is 0.67. And about the only time it matters to get it any closer is when using stubs. But that's another band-aid for use where there's nothing else that can be done, like AM broadcast towers or inaccessible antennas, or antennas can't be modified. So there's the skinny on getting the exactly correct transmission line length. Okay, BYP. Merry Christmas.